All right, so we're going to, in the rest of this section, look at radicals where the radicand, it is not a perfect square, it is not a perfect cube. What must you do? What must we do to simplify that? So, two ways that we can simplify this. One way is listing the prime factors, or using the prime factorization tree. Or the second way would be listing the factors of 18. So let's look at each way, each method. Okay, the first method, I'll just say, we'll call it A, just listing the factors. So we want to find factors of 18. And the factors are 1 and 18, 2 and 9, 3 and 6. And as you list the factors, you want to look at a set where one of the factors is a perfect square. And you notice where 9 is a perfect square, you have the factors of 2 and 9. So what you want to do is list the factors of 2 and 9 and then circle the perfect square factor, which is the 9. This is the factor that you're going to take the square root of. Okay. Now we would take the square root of 9, tell me what it is, and we're going to bring it on the outside of the radical, and that is 3. The 2 will stay under the radical sign because 2 is not a perfect square number. So our solution is 3 square root of 2. Okay, so this is one method, listing the factors. And I don't have a problem with this, but sometimes you do have factors. When you list the factors, you have several sets where those sets may have more than just one perfect square root. So finding which one it is, that becomes the issue. Now B, um, listing the prime factorization or prime factors using the prime factorization tree, where we start off with 18. Here we have 3 times 6, so you can use 2 times 9, it doesn't matter. Where we're going to branch, and then 3 is prime, so I'm going to circle that. Let's branch off 6 because we can find factors of that, and 6 being composite, we have 2 times 3. So we want to find the prime factor. We're going to list the prime factors, which we found. We have 2, 3, and 3. Now the prime factorization method, this is probably my favorite one because I see less errors when students are using this method. It may be more work, but you're able to see which factors need to be taken out. So how do you determine which factors are going to be taken out? Well, one, it depends on the index. And because our index is 2, our goal is to group any pairs that we see under the radical sign. If the index was 3, then we would have to find groups, we're circling groups of 3. So here's my story, and I'm sticking to it. Let's just say that our prime factors are in jail. And the only way that they are able to come from out of jail, outside, is they can only come out depending on the index. And because our index is 2, our goal is to circle all the pairs. Well, we have a pair of 3s. So um, we're going to bring the 3 on the outside. One other another reason that I like this particular method, because it's telling you the factor that you're going to bring out. You don't have to second guess, is this a perfect square number or not? We're going to bring this 3 on the outside of the radical, and then the 2 would stay under the radical because it wasn't paired with anything. So you have we have the same solution, just different ways of finding the answer. So the choice is yours now, but I will say for the rest of the lesson, I'm going to use the prime factors method. Okay, listing the prime factors. Let's do it that way. Um, I'm going to use that method because, or this method, because, like I said, I see less errors, and then it gets you to thinking about the factors or how to find the prime factors of a given composite number. Next example, we have here 3 times the square root of 63. So what we want to do is list the prime factors for 63. Okay, so we have 7 times 9, 7 being prime. We're going to branch down 9. We have 3 times 3. Okay, so these are the prime factors for 63. On the outside, you have a factor of 3. That's fine. Whatever we bring from under the radical sign to the outside, we're going to multiply this 3 to it. So let's list the prime factors for 63. We have 3 times 3 times 7. Because the index is 2, we're looking for pairs. I see a pair of 3s, and we're going to bring that on the outside, from under the radical to the outside. As we bring it to the outside, then we're going to multiply that 3 that we brought from under the radical to the 3 that was originally there. So we have 3 and then the square root of 7. And that is our answer. Next example, the square root of 11. So I'm going to show you using the prime factorization method, where we're going to write 11 or y 11 times. So y was written 11 times. These are the prime factors. Now, because the index is 2, we want to group in pairs. We have 1, 2, 3, 4, 5. We were able to circle 5 pairs. So what this is telling you is that we're going to bring y out 5 times. And we're going to then, what's on the outside of the radical, we're going to multiply what is outside the radical. So we're going to multiply y 5 times, and then that would give us y to the 5th, and then what stayed under the radical sign? Just the y. So we will write y to the 5th times the square root of y. So this is one way that we can do this. Okay? Or we can say, how many times does 2 divide into 11 evenly? Well, we have 5. We can use some long division this way, which is 5 times 2 is 10, and we have a remainder of 1. So the quotient area, this tells you how many factors that are on the outside of the radical. So we had 5 y's that were on the outside, and then the remainder is the number that stays under the radical or inside the radical. We had one y that stayed, or let's say inside the radical. Okay, so this is one way of doing that. You can divide it, or you can show me. Showing, like I said, me showing you this way, there are a lot of less errors. Now, what if, just to extend this out, what if we had the cube root of y to the 11th? So here again, I'm going to write y 11 times. And cube root. So we're going to group this time because the index is 3. We're going to group in threes. How many groups do we have? 3. So that means y is going to go on the outside 3 times. And then we multiply. You have y cubed times the cube root of what's left under the radical sign, y squared. So this is how you would use the index.